So in today's lecture we are going to talk about change of variable in double and triple integral. Well, unlike one variable case, to prove the formulas for the change of variable in the double integral is conceptually a bit difficult. So what we would try to do is, we will try to explain what does change of variable formula mean and try to give you a neat formula based on which we can calculate certain integrals and use the change of variable formula. Well, in the one variable case, we know that this formula is true, that in integral a to b fx dx is integral c to d f of gt times g prime t dt, where g of c is equals to a and g of d is equal to b, and g is a differentiable function with g prime t not equal to 0. This is the classical formula of change of variable in one-dimensional Riemann integration. Now we want to have a generalization of this for double integral and the triple integral. So the situation here is something like this, that let us say that this is the uv plane and this is the xy plane. So I would write this as xy plane. It means points of coordinates little x and little y. This is uv plane. Here points of coordinates little u and little v. So this uv plane is just a replica of the xy plane. Now suppose on the uv plane I have a domain T, and on the xy plane let us say I have a domain S, and I am interested in this double integral, integral over S f of xy dx dy. Now suppose I have a one-to-one map here, it's 1, 1, that means it is injective and onto map. Then I can say that this Ax is given by a function capital X including two variables u and v, and little y is a function of two variables given by capital Y, and the variables are u and v. Okay, so I can say that xy is capital X of uv. This would be very clear when I look at examples. Capital Y of uv. Since I am dealing with two variables, when I change from one domain to the other, the new coordinates which are appearing, that is x and y, they are functions of both the variables which occurred previously, that is little u and v. That is the whole point of writing little x as a function of u and v and little y as a function of u and v. Okay. Once I have this, then I look at the following. I will denote it by mod j u v. What is this quantity? It is the modulus of the determinant of the following quantity: del x del u, del x del v, then del y del u, del y del v. That is, look at the function capital X. It is a function of two variables u and v. I look at its partial derivatives. So there are two partial derivatives, one with respect to u, one with respect to v. I put them in the first row of a 2 by 2 matrix. Then I look at the function capital Y, it is a function of two variables u and v. I look at the partial derivatives, I put them in the second row. Then I calculate the determinant, and then I take the modulus of that determinant. That is what is denoted by mod juv. And then the change of variable formula is written as follows. The formula is the double integral over S f x y dx dy. This is double integral over t, that is the domain of the transformation, f of x uv y uv, then mod j uv, then du dv. Notice here that modulus of juv essentially plays the role of this quantity g prime t which is appearing. Okay, this quantity is actually replaced by mod juv. That is what is meant in this formula. Now we are not going to prove this formula. Let me just assume this. Well, for this certain things, certain hypothesis I need, that is that x and y, they have continuous partial derivatives. Otherwise the mod juv won't make sense. So for any arbitrary kind of transformation I cannot work. The condition on the transformation is that the partial derivatives exist and they are continuous. Now based on this formula, let me try to look at example. So as an example, I would say find the area of the region S in the xy plane bounded by the hyperbolas xy equal to 1, xy equal to 2, and the curves xy square equal to 3 and xy square equal to 4. So essentially what I need to calculate is double integral over S dx dy. Now you can see that given the conditions of these hyperbolas and the curve, it might be complicated to find the limits of x and y which describes the region S. So because of that, what we do is, to make it simpler, we want to pass on to the change of variable formulas. So what I do is, I define, let us say, u equal to xy and v equal to xy square. Suppose I just define this. Now what I want to do is express x and y in terms of u and v. That is very simple. What I do is, I look at u square, which is x square y square. Then I define u square by v. What I get is x from the above formulas. And once I know this, it is very easy to calculate y, or straight away you can just look at v by u what you get is y. So here what is happening is x equal to capital X of uv. So what is this capital X of uv? I again look back at the formula. It is u square by v. So this is u square by v. Similarly, y, which is supposed to be capital Y of uv, I can see from the previous formula, it is this quantity. So I get v by u. Once I know this, I can calculate the Jacobian, that is the first thing. So mod j uv. So this is modulus of the determinant of del x del u, then del x del v, then del y del u, del y del v. So it is modulus of, now I can calculate what is del x del u, that means the partial derivative of this, that means twice u by v, then minus u square by v square. Then the second function, I have to differentiate with respect to u now, so it is minus v by u square. Then I have to differentiate with respect to v, then I get 1 by u. Then I have a modulus. I can try to calculate this. So what I get is modulus of twice 1 by v, because twice u by v into 1 by u, that means 2 by v, then minus u square cancels, I get 1 by v. So I get mod 1 by v. So this is the Jacobian. Now I look at the integral. I need the limits of u and v. That was the whole point of going to this change of variable, because the limit of x and y, which describes the region S, turns out to be complicated. So we are looking at the limits of u and v, perhaps that is simpler and describes the transformed origin. So we look at the formulas of u and v here. Let us see, the hyperbolas are given by xy equal to 1 to xy equal to 2. But according to my substitution, xy is equals to u. So u varies from 1 to 2. Look at v. V is given by xy square, and xy square varies from 3 to 4. So u varies from 1 to 2 and v varies from 3 to 4. So u varies from 1 to 2, v varies from 3 to 4, dv du. Now what remains is the function, but the function is the constant function 1, fortunately. So I don't have to look at the function part. All I need to now incorporate is the Jacobian. But the variation of v is from 3 to 4, so v is always positive. So modulus of 1 by v in this case is same as 1 by v. So I have to integrate this one. Apply Fubini's theorem. I can first integrate the v variable that produces log v, that means log 4 minus log 3. So it is integral 1 to 2 log of 4 by 3 du. But in the integrand there is no u, so I take it out of the integral, and what I get is integral 1 to v du, which is 1. So final answer is log of 4 by 3. So this is how one uses change of variable formula. Now there are certain standard change of variables which you usually do in certain problems. For this, it is always good to know what is the Jacobian of that change. This quantity mod j of uv, which I am writing here, this is called the Jacobian. Okay. So one such very useful transformation is changing from Cartesian to polar coordinates. So polar coordinates. So we know what it is, that x is given by r cos theta, y is given by r sine theta. Okay. So that means it is capital X of r theta instead of u and v. It is capital Y of r theta. Okay. And then to calculate the Jacobian, what I need to look at the determinant of del x del r, then del x del theta, del y del r, then del y del theta. So I would write it down here. So if I look at del x del r, I get cos theta. Then when I look at del theta, I get minus r sine theta. Then in this case here I get sine theta because I am differentiating now y with respect to r. Then if I do it with respect to theta, I get r cos theta. So the determinant produces r times cos squared theta plus sine squared theta. So it is just r. I don't need to take modulus. Here I always take r bigger than 0 and 0 lesser equal to theta strictly less 2 pi. So the Jacobian determinant under this change of variable dx dy always changes to r dr d theta. Now whenever, usually the thumb rule is, whenever you see the integral where the quantities x square plus y squares are appearing, then it is better to shift things to polar coordinates. So we show you this by an example. So here the problem is to find the volume of the sphere of radius a. Then I know very easily that this volume V by symmetry is given by 2 times double integral over S, then square root of s square minus x square minus y square dx dy, where S denotes the upper half of the sphere. So what is S? Such that x square plus y square is lesser equal to s square. Since I am taking the positive square root, I am actually finding the volume of the upper half of the sphere. So what I am finding out is this. But since I am multiplying by 2, I am going to get the volume of the whole sphere anyway. Now looking at this integral, I can very easily see that it is the situation where I should use polar coordinates. So use polar coordinates, x equal to r cos theta, y equal to r sin theta. Then what do I get? Then this integral in polar coordinates is 2 times double integral 0 to a, then 0 to 2 pi, 0 to a is the variation of r, 0 to 2 pi is the variation of theta, square root of s square minus r square. Now comes the Jacobian, that is r dr d theta. Okay. Now since there is no theta involved in the integral, it is only the integral in terms of r, the theta integral I can calculate by Fubini's theorem. So it is 4 pi times 0 to a square root of s square minus r square into r dr. Okay. Now this integral can be easily calculated. You put just, let us say, s square minus r square is equal to t, then minus twice r dr equal to dt. That means r dr is equals to minus half dt, and the limits of integration changes from, if r is equal to 0, then t equal to a square. If r equal to a, then t equal to 0. So finally what I get is that this is 4 pi times integral a square to 0 root t times minus half dt. Okay. So what I get here is then 4 pi divided by 2 integral 0 to a square root of t dt. Final answer then is 4 pi by 2 t to the power 3 by 2 from 0 to a square into 2 by 3. So what I get is 4 by 3 pi, I get 4 by 3 pi, then t to the power 3 by 2, instead of that I would put a square to the power 3 by 2, so a square to the power 3 by 2. So it is 4, sorry there is a 3 here, so 4 by 3 pi a square to the power 3 by 2, that is 4 by 3 pi a cube. That is, we already know is the volume of a sphere. It comes out of double integration and it becomes very easy just because of the change of variable formula. Now we will slowly turn ourselves towards the integrations of 3 variables, and again we will try to go to the change of variable formula for that. Now we will be very brief about the construction of Riemann integration in 3 variables because it is very analogous to the 2 variables. So let us go by that. Triple integral now. So in the case of one-dimensional integral, we started with intervals. In two-dimensional integrals, we started with rectangles. In this case, we are going to start with cubes. So suppose f is a bounded function on the cube AB is a bounded let's not really demand continuity on these functions, because just for bounded functions one can define Riemann integration, but in most of the cases we are going to deal with continuous functions. So I don't think there is any harm in putting the notion of continuity in the definition also, that it is for the bounded continuous functions we are looking at the construction of Riemann integration. So what you do is, now first take P1, this is a partition of AB, then P2, this is a partition of CD, then take P3, this is a partition of EF. Okay, then I define Mij to be infimum of f x y z, where x y z belong to xi plus 1 cross yj plus 1 cross zk plus 1. So these partitions, let us assume that they are given by x1, x2, xn, let us say this is given by y1, let us say x1, that is better, up to ym, let us say this is E equal to z1, zl, let us say. Well, this f one should not confuse with the function f, so let me change this, let me call it p. Okay. Then one can define capital M I J K analogously. Then you can construct U P1 cross P2 cross P3 F. One can construct L P1 cross P2 cross P3 F. Just by looking at this supremum and infimum, then I can look at the infimums of the UPFs, I can look at the supremum of the UPFs varying over all partitions. If these quantities turn out to be same, then we say f is integrable. Which is analogous to the double integration. And as we have seen in the case of double integration, that it is actually the Fubini's theorem which helps us how to calculate integrals. So similarly here we will need a Fubini's theorem for triple integrals also, and we have defined it for cubes. As in the two-dimensional case, we had defined it for rectangles. For general regions, general bounded regions in 3 dimension, what do? You find a cube which contains that region and extend f to the whole of cube by making it 0 outside the region, and then proceed with the constructions which I have given above. So that defines the triple integral for bounded regions, which are more complicated than the cubes. And here we are going to need some analog of Fubini's theorem also in the 3 dimension, that I am going to explain now, and that is going to play the fundamental role while working out triple integrals, and then we will shift to change of variable formula. So let us start first with Fubini's theorem. So suppose D is a region in 3 dimension, it is bounded by two surfaces, let us say z equal to f1 xy and z equal to f2 xy. f1, f2 both are continuous functions, of course, and on the side by a cylinder C. So on the side by a cylinder C which is parallel to the z axis. So in picture what I mean is something like this. So this is the cylinder, this is x axis, this is y axis, this is z axis, and there are some surfaces. This is z equal to f1 xy. Of course, it may not be bounded, it might go on, but as far as my purpose is concerned, I am just looking at the intersection portion, and let us say z equal to, let us call this f2 xy, this is f1 xy. Okay. So this is the picture. So my region of integration actually is the in-between portion. So to calculate integrals of functions over this region, what I do is, so this region is called D. The portion below, which is the projection of that region on the xy plane, I call it R. So you get a portion on the cylinder, just project that portion on the xy plane, it will produce something in the xy plane, that is what I call R. Okay? So formally D then is x, y, z such that xy belongs to R and z satisfies f1 xy lesser equal to z lesser equal to f2 xy. Okay. Now if I want to integrate a function over D, so I would say triple integral over D capital F, okay, x, y, z dx, dy, dz. How do I integrate this? The idea is you look at double integral over AR of the function integral f1 xy to f2 xy f of x, y, z dz then dx, dy. So that is, what you do is, look at the function. In the expression of the function, you keep your x and y fixed. Just view it as a function of z. Already some limit is given to you, given on xy. Once you fix your x and y, f1 xy and f2 xy are just two numbers. Now you integrate the function f xy fixed as a function of z. Put the limits, that gives you a function of x and y. And now you are integrating that function over R, that is a double integral. So the triple integral, after first using one integral with respect to z, reducing it down to a double integral. And for double integrals we know how to compute things. Maybe you need Fubini's theorem, maybe you need change of variable or something like that. Okay. So this is how we are going to compute certain triple integrals. So let me show it by an example. So let us try to compute triple integral over D. Let's take a very simple function, x dx dy dz. The whole thing is, what exactly is D? Well, I will describe what is D. Where D is the region in space, that means in 3 dimension, bounded by the planes x equal to 0, that means the yz plane, y equal to 0, that is the xz plane, z equal to 2, that is parallel to the xy plane, and the surface z equal to x square plus y square. Okay. So first let's try to have some idea about, so this is z axis, this is x axis, this is y axis. So let me write x here, z, y here. Okay. So this x axis actually denotes the plane y equal to 0. So I will, let us say this height is 2. So I will draw lines here. So my region D I can very easily draw now. This is the intersection of z equals to x square plus y square. So what is the region now? It is actually the inside portion. So how do I draw it? Well, it is Okay. So this is the region on which I want to integrate my function x dx dy dz. Certainly I am going to use Fubini's theorem. For that, what do I need is the projection of this on the xy plane. So if I project it, I am going to get some portion of a circle that you can very easily see. It is going to be this circle, that is x square plus y square equal to 2, because this height is 2. So the projection is this. That is going to be my r. So what should be the integral then? So let me write down what is d again from this picture. D then is x, y, z, such that how much x vary then? X vary from 0 to root 2. Okay. From here x equal to 0, I can come up to here, that means y equal to 0, that means x equal to root 2. I am in the first quadrant. Okay. So 0 lesser equal to x lesser equal to root 2. Based on that, I get my y, that is 0 lesser equal to y lesser equal to square root of 2 minus x square. This portion actually gives me r. That is the parametrization of the projection. And then what is the variation of z? It is x square plus y square lesser equal to z lesser equal to 2. So in this example, my function f1 is actually x square plus y square. So f1 xy is x square plus y square. And my function f2 xy fortunately is a constant function 2. Okay. Now once I know this, then I can try to calculate using Fubini's theorem. That means triple integral over d x dx dy dz. This is same as double integral over r, then integral x square plus y square up to 2 x dz, then dx dy. I can write it more formally, saying what exactly r is. R is 0 to root 2, then 0 to square root of 2 minus x square, then x square plus y square to 2 x dz, first dy, then dx. Notice, once you fix your x and y, then look at the most inner integral. There is no x here, there is no z in the integrand. So this integral is z, just 2 minus x square plus y square. So it then comes out to 0 to root 2, then square root of 0 to square root of 2 minus x square, then 2 minus x square plus y square, that means z integral I have performed, then dy dx. This now can be easily computed by using the standard Fubini's theorem and two variable. So this is the way we usually try to go about triple integrals if there is no change of variable required. So the method is just, if you have a body of the form that it is bounded by two surfaces contained in a cylinder whose axis is parallel to the z axis, just try to find the projection of the body. That gives you a two-dimensional integral, then calculate the variation of z. So calculate the z integral first. By Fubini's theorem, this then reduces down to a double integral, for which we already have the method. So that gives you how to calculate the usual triple integral. Now let's try to go to more complicated triple integrals where we will need the change of variable formula. So let us go to the change of variable formula for triple integrals now. The formula is very analogous to the two-dimensional case, only to calculate the Jacobian you have to calculate more, that is expected. You will get a 3 by 3 determinant now. So the usual formula looks like triple integral over S, f of x, y, z, dx, dy, dz. Okay. this is same as triple integral over t. Now f of, let us say, x u v w. In the two-dimensional case, x was a function of u and v. Here everything is going to be a function of three variables because I am in space. So the extra variable is w. Then y of u v w. Then z of u v w. Then the Jacobian, which I will denote as mod j u v w. Then du dv dw. Then what is mod j u v? That is again the modulus of certain determinant, analogous to two-dimensional case. It is del x del u, del x del v, del x del w, then del y del u, del y del v, del z del u, okay. So this is the Jacobian which one needs to calculate. You can take it just in the spirit of two dimension. It is just the analogous thing. So here, as an example, what I would like to do is polar coordinates in three dimension, which is slightly more involved than the two-dimensional case. So here, what are the parameters? Suppose I take a point P here. Then P has a distance r from the origin. This is, let us say, x-axis. Let me draw this. Let us say this is the x-axis, this is the y-axis, this is the z-axis. Then this point P, wherever it is, it makes certain angle with z, okay. So this is an angle, call this phi. Now I project the point on the xy plane, okay. Then this distance I can certainly calculate, since this is phi, and then if I call this point some a, let us say, okay, then this is 90 minus phi, this is pi by 2 minus phi. So this point A then is clearly r sin phi. What is the z coordinate of the point? That is this distance. It is very easy to calculate. It is r cos phi. So the point, if I look at its Cartesian coordinates, then its z axis is r cos phi. So let me write that down first, that z equals to r cosine phi, that I found out. Now what is the x coordinate of this? That I need to find out. Now I need one more variable. I call this angle theta. So theta is the angle which this projection makes with the positive direction of the x-axis, okay. Then it is very easy to see what the Cartesian coordinate is. Then x is a cos theta. But what is a? A is r sin phi. So it is r sin phi cos theta. Then y is certainly a sin theta, that is r sin phi sin theta. So what are the restrictions? That r is always bigger than 0. I will be using that. Then for phi, I have 0 lesser equal to phi lesser equal to pi, because it can come from top to the bottom only. So the angle which it will be making is up to pi by 2. And then theta is our usual thing, that 0 lesser equal to, sorry, this is phi. So phi varies here clearly from 0 to pi, because the point it comes from the top to the bottom. So the angle it traverses, it's 0 to pi. Then I come to theta. Theta is our usual thing. It varies from 0 to 2 pi. Now one needs to calculate the Jacobian of this, which I leave as an exercise to you. Show that modulus of j r theta phi, this turns out to be r square sin phi, okay, once I take the modulus. So in the two-dimensional case, it was just r dr d theta. The angular variable did not matter at all. But in 3 dimension, that is not going to happen. You see that r square comes certainly, but sin phi also comes. What does not come is theta, but phi comes. Okay. Now let me go to an example of a problem where change of variable formula is needed. So I just say let us say R is this. It is all x, y, z such that x square plus y square plus z square is less or equal to 4a square. That means I am inside a sphere of radius 2a and I take z bigger than or equal to a. So the region I am looking at is this. So the above portion of this smaller sphere, that is what I am looking at. Okay, and let us say I want to integrate triple integral over r z by x square plus y square plus z square whole to the power 3 by 2 dv. That is dx, dy, dz. That is what I mean, the volume integral. Now, once you look at this quantity, you immediately understand that you need to go to the polar coordinates because x square plus y square plus z square is appearing here. So once you go to the polar coordinates, here the only thing is you have to calculate the variations of phi theta. Now look at the region on which I am integrating. Theta is certainly going from 0 to 2 pi, there is no problem with that. But phi starts from 0 and stop at here. Okay? So you need to know what is this phi. Well, that is not very hard because you know what this height is. This height is actually a and this portion is 2a. So that will tell you that this phi which I am looking at, this is actually pi by 3. Okay? Because cosine of phi is turning out to be half. So once I know that, then I can get the variation of r also. So in polar coordinates now, in polar coordinates, the integral is, let me write the 3 integrals, I will put the limit later. Then z means r cos phi, I know that, divided by x square plus y square plus z square to the power 3 by 2, that means r cube here, then r square sin phi. Dr d theta d phi. So I can put the theta here 0 to 2 pi. This is the variation of theta. So d phi d theta. Then the variation of phi, which as we have seen, it is from 0 to pi by 3. Then a little calculation regarding r is needed, which I urge you to do it yourself. That turns out to be a sec phi to 2. It's not really very difficult, just look at the picture, then you see the variation of r which comes out. Once you do this, then actually this r goes away, you are finally landing up with 0 to pi by 3, theta integral also I can manage, so it is 2 pi, so it is 0 to pi by 3 integral a sec phi to 2. What you get finally is cos phi sin phi dr d phi. In the integral there is no r, So what you are landing up with now, 2 pi integral 0 to pi by 3 cos phi sin phi into 2 minus a sec phi d phi. Okay. This is the integral you need to calculate, which is a typical trigonometric integral which can be calculated very easily. So in most of the cases, when you when you have the quantity x square plus y square plus z square in the triple integral, you should go for the polar coordinates. All you have to be careful is that given the region, what is the variation of r, theta and phi, that you have to calculate. And for that, it is always good to visualize the given region in a geometric way so that you can see from the picture what it is going to be. So this is more or less what I wanted to say about change of variable formula, double integral and triple integral. Now from now onwards, we will slowly shift towards the proof of the fundamental theorem of calculus in case of double integrals and triple integrals. That means those are the famous theorems called Green's theorem, Stokes theorems and divergence theorem. Those are going to come in the next few lectures as the analogues of the fundamental theorem of calculus.